Hi, Eleanor. All right. So let's go ahead and get going here where we left off the other day. Two-dimensional kinematics is, again, this one should ideally go quick. These are the same as they were last time. They are, as it says up here, pretty much identical to that in one-dimensional. The main thing to understand is that the y direction does not affect the x direction. And while it's not up here, let's go ahead and throw this in there. The z direction does not affect the y or the x. They can be independently combined together with those methods that we talked about for vectors in 3 dimensions. And there you go. So the position vector r is a combination of x and y. And this is, to give you an idea that you readily know already, okay, here we go. R would be something like 5 meters at 53.1 degrees. There's R is equal to 3 meters I hat plus 4 meters y hat is essentially the mathematical definition of what that says. Okay, anytime you should see R, that's polar form. You should think magnitude and angle. And why is that I hat? Sorry, screwed up. I used y. Sorry, I'm used to doing that in physics 1. I hat and j hat. What are those there to do? Those are there to indicate direction. I hat being A, go along the positive x-axis, and j hat going positive along the y-axis. As such, velocity vector can be found from the derivative, okay, of these two. If you don't know what I mean, I gave an exact example on Friday where I went all over this. You can watch that video to get that general idea. Since acceleration is constant, now when is it going to be constant? Well, we are still locked into kind of projectile motion in general, and projectile motion, what is the main acceleration going to be from? Yeah, gravity, and gravity is constant. So because of that, we can kind of lock in this exact old equation that we used in generic kinematics before. All right, so RF equals RI plus VIT plus 1/2 AT squared. Again, this is a very familiar equation. This is the exact same equation, but anytime you see R, or in this case VI, you have to know, and A, what's buried inside of all of them? The X and the Y, correct, okay? This, for example, could be something to the effect of that 3 meters I hat plus 4 meters j hat could be buried inside of there. And I could say something to this effect. This could be 2 meters per second I hat plus, let's go minus 1 meter per second j hat. What does that mean is going on at the beginning?
It's going
Start with this.
Going up.
It's at 3, 4.
It starts right here. Okay, so something on a hill or something to that particular effect. Okay, and
It's moving right.
I'm sorry, it's hard to see that. Let me write that a little bit bigger.
2 meters a second. It's going 2 on the X and down 1 on the Y.
So in other words, that's its initial velocity, right? Now, you're pretty sure you know what the acceleration vector is. Okay, so you tell me what should the acceleration in standard be? Draw it in terms of its components. Discuss quickly in your group, and we'll be right back after these messages. What should the acceleration vector be drawn as? If we are dealing with standard projectile motion.
We're gonna do like wind resistance, right? Or air resistance, right? In here.
I don't know if it's in this chapter, but yes. Okay, so there it is. I got you started. 0 meters per second, what? I hat minus G J. Correct. Of course, G has the meters per second squared buried inside of it. All right. And this is the exact same sort of thing that we're seeing right here. Okay, the velocity vector can be represented by its components. According to this right here, what happened to, what was the initial velocity? It was up and to the right. Okay, you can imagine overlaying this on a position. This is me throwing a ball upwards right here. Obviously, this is not a fake, this is a fake planet, but according to this particular planet, the direction of acceleration is up and to the right. So what do we expect to happen in the x and the y? We should increase in both. Increase by how much? Well, acceleration by definition is the change in velocity over time. So x would be just the acceleration in the x would be the ratio of how much velocity will change in the x over time. So simply multiplying that ratio by the amount of time would give us the total change in velocity in the x. That's what this is here. And change in velocity in the y. And of course, to get the finals, you take the initial, you add the change, and that gives you your final at the end. So it would make sense that this particular object is going faster in the x and faster in the y, given that. I should be able to give you just generic velocity vectors, and you give me a rough idea of what's happening. For example, if I said velocity initial here is up in the first quadrant, and acceleration is down to the right, okay, in the next few moments, okay, don't worry about long term, but in the next few moments, what should happen to velocity in terms of its components? Discuss quickly. We'll be right back in about 20-30 seconds. All right, go. Seems like you guys are good.
Get bigger horizontally. And
Yeah, so you get faster in the x and should slow down in the y initially until
there's nothing to know. Or until like the y goes negative.
the y goes to, well, you're correct. So the y would stop, get 0, and then of course go negative beyond that. Very good. All right, and then the position vector works extraordinarily similarly. If we combine it into kind of like all three vectors, what we have here is we have the initial position. This is like my 3x, okay? This is the change in position as a result of that initial velocity. If there was no acceleration, that's where we would end up, okay? Excuse me. But this person is, of course, accelerating up and to the right, which since the velocity is here, we expect them to speed up going left and right. And so this takes the change in velocity, so the average change in velocity, and multiplies by time. Questions, concerns? Okay, so all of those are position vectors. Initial position, change in position due to initial velocity, and change in position due to acceleration. If there were no acceleration, this would not be here, okay? If there was no initial velocity, you'd have just those two right there. Okay, various starting positions and initial velocities can be chosen. Note the relationship between changes made in either position or velocity and the resulting effect on each other. So in other words, just note what the initial velocity is here, the initial velocity is here, and what effect they have on particularly others. Same thing with the acceleration. All right. Projectile motion, you know this. It's moving in the two-dimensionally pretty much, and we're just dealing with gravity. Assumptions of projectile motion: free fall acceleration is constant over the entire range of motion, and it's directed downward. Is this 100% true? No, this is an approximation. What technically happens to the direction of acceleration as you continue? It does move, yes. Now, over a small enough range, is it fair to approximate gravity is perfectly downward? Yes, 100%. Over a large enough range, we have to deal with the actual curvature of the Earth. Who would have to deal in projectile motion with the curvature of the Earth? Sure, that's not, I mean, people on projectile motion. Well, actually, I'm going to say no, because if we're talking astronauts, they're not dealing with projectile motion. They're dealing with more than like circular motion. So who would deal with projectile motion but still have to deal with the curvature of the Earth? Yes, it's not an example I was necessarily going for, but yeah, that you do get, by the way, you'll see this, for example, if you've ever on a flight over to Europe. If this is, you know, America right here, okay, you start here, and this is, of course, Europe over here. One weird thing, a lot of times they'll have the flight path on there, and the weird thing that you'll see is this. To which you go, wait a minute, I thought that I thought the shortest point between 2 points is a straight line. And it is, except we are dealing with the curvature of Earth, so actually that is the shortest path for the plane to travel, which is why they do what it is they do. That's true. That's not what I was going for, but I like that. Who else?
People who shoot missiles.
Not quite what I was going for either.
Guns?
Sort of. I was thinking snipers specifically. Snipers
Like the
do in
Coriolis
fact have
effect?
to deal 100% well. They have to deal with two major things there. One, drop of the Earth itself at a particular distance. I think that the rough. Well, we can do this. Okay? Do you remember what the radius of the Earth is?
Yeah.
Okay. 4,200 miles. Okay. So that being said, quickly calculate what is the circumference of the Earth.
Said how many miles?
4,200.
26,389 miles.
Okay. So that.
Wait,
you're not doing it.
diameter or the radius?
You can do it either way as long as you do it correctly.
I know that's what I'm trying to show.
Either way is fine. 4,200 times 2 pi or 8,400 times pi are the same thing.
Okay, so you did get the radius.
I did get the radius. 26,300, yeah, and 89. All right, take that number and divide by 360. What does that tell you? What does that tell you?
That tells you the amount of miles that one Earth is in
1 degree of Earth, correct. Divide that by 60.
after a minute.
That is literally how far the Earth will travel in 1 minute's time, rotating around itself, which is also why the direct reason, if you'll remember us talking about a minute of a degree, that's why it's called a minute, correct? So if you divide that, you'll get that it's only 1.22 miles. Generally speaking, obviously we're talking in miles here, but if you are actually trying to hit a particular target, you're going to want to get down to feet and potentially inches. So obviously, smaller amount of angles are going to have an impact. So if a person has to fire a gun 1 mile away, roughly speaking, they're dealing, I mean very roughly, I get that, but they're dealing with about a minute of degrees of Earth. Now, is that going to have a huge impact on the drop in miles? No. Is that going to have a huge impact on the drop in feet? 100%. One of the most basic ways, and this just boggles my mind, that human beings struggle with this, to tell somebody that there is a circular Earth that we're dealing with, is the fact that you can only see about 5 miles on a clear day. And that directly results from how far you stand above the ground. Maybe you can see further on a clear day than I can, but not all that far. So from that, you can sort of get a basic ratio. You can go, hey, at about 5 feet, 5 miles this way drops by about 5 feet. Because that's about how far it goes before I can't see anymore, roughly speaking. Okay? So yes, snipers do in fact, having to deal with feet and the like, do have to deal with this particular effect. All right. We will once again assume the air friction is negligible. If it says projectile motion, you can make that particular assumption. We've done this 100 times. You'll notice that in this one, the x is staying exactly the same. The y is changing due to the gravitational acceleration. I'm not going to go through that. Vertical should be 0 at the top. Acceleration is not 0 anywhere along its path. Is the object's velocity ever 0 in projectile motion? No. Its velocity is never 0. Velocity in the y is 0, of course, at the top, but it is still moving in the x. Analyzing projectile motion, you have your exact same equations, initial velocity, final velocity. We've done all this mess. You guys have probably already been practicing this. This is a great picture to recognize this guy right here. If you stop at 0 right here, this is, some of you might remember a problem from last year that a lot of people struggle with, and I think it's the one where, you're trying to figure out how fast it is to get on top of like a shelf. It was a test problem in I know it's been a minute. But what a lot of people accidentally do at the very beginning is they it's the jelly bean problem in Shaq. You're trying to figure out what angle to fire at in order to get the jelly bean to land on top of Shaq's head. Do you remember this ish? Okay? And so what a lot of people will do is they'll take this distance, they'll take this, that's right. I screwed up. Erase that one. Thank you. They will take this distance and they will go, oh, and they'll make a triangle out of it. But that does not work because as you can see right here, if you were to fire directly at Shaq, if I was to fire directly at the top of this particular path, due to this, the change in position due to gravity, there is no way that I would actually land on Shaq's head. I would have to go before. That's a whole thing. But yeah, so we see our final is equal to this plus this, assuming, by the way, that our initial is, say that a little bit differently, 0, 0. But yeah. Okay, range and motion. I hate the range equation. We will not use it in here because it's not a new equation. It's something that we already know. Basically, what you're going to do to get the range equation is simply, there is the range equation. Actually, that's the maximum height equation. Well, there's the range equation right there. Let's develop those quickly right now. So let's start off with how we get that particular equation. So how you get that particular equation, I'm going to have you develop it right now, is I'm going to tell you that your initial velocity is VI, because of course it is, fired at an angle of theta. Okay? And of course, acceleration is negative g. And from that, I would like you can get anything else. I'm not saying this is it for your given and find, but these are the things given to you in this problem. I want you to calculate an equation to get the max height, knowing full well what the final answer is, but let's see if you can't get there yourself. There is a value in the given that obviously you can figure out to get max height. This one's easy. Sorry, relative to the other one. I'm not saying it's the easiest thing in the world, but easier than I remembered that one. got this one?
No.
You want help? Time, help, or done?
Help.
Help. Okay. So what next assumption should you make here?
Yeah. Y is 0.
You have y is 0. Okay. And anytime you have one of these, just set it up like it's just a straight up normal problem. So what I'm going to do is just look entirely in the y. Now, I don't know that ahead of time, so oftentimes I set up everything. So I go VIY is equal to what?
VI sine.
Correct. VI sine theta. Okay. Acceleration is negative g. Yes. And delta t I don't know, and delta y I'm calling h. Yes? And I can put the x stuff over here, but I'll just give you a heads up, we don't care. Because we don't need anything in the x. And what you'll notice in this particular equation is I have 4 variables in the y, including the one that I want, which is this guy right here. So I'm just going to go ahead and use that equation that has those 4. So what is that equation?
Is it the x squared equals vi squared plus 2a delta x?
Yep, vf squared, vi squared plus 2a delta y. Remember, anytime dealing with the y and the x, it's much more valuable. It's not going to mess you up as much as long as you keep those variables in that spot. And let's do this. This is vfy, viy. So what is vfy?
0.
0. Okay, so that's 0. What is viy?
Vi
Theta. And since that's squared, this will be squared and that will be squared. Right? Plus 2, what was my acceleration? And what are we calling delta y? And so now we simply just solve for h. So literally all it is. We take this piece, subtract it on the other side, divided by 2 negative g. My negatives nicely cancel, and there it is. There's the equation that they gave us. Now, where are you guys getting hung up on?
I just didn't think to use the equation.
Yeah, that's exactly what you have to do. Okay, you're using the equations that are already in place in order to combine them together. So let's have you do it now for the range equation. Now, before you do the range equation, it is a little bit more challenging, but understand a couple of assumptions about the range equation. Okay, number 1, the range equation, and you can use this for 2 methods. Okay, there are like 2 ways that you can use this that I'll show. Okay, the first thing to understand is that the path will start and end at the exact same height. It's assuming the object starts on the ground and ends on the ground, which gives you some information. Well, technically gives you 2 pieces of information, of which you only need 1. Okay. Once again, we will assume the following. We will assume it's fired at vi at an angle of theta, and that acceleration is negative g, and I'll let you figure everything else beyond that. I do need to tell you one other thing. It is a trig identity that you have to use to do this, kind of simplify it well, and it is this one. 2 times cosine of an angle times sine of an angle is equal to sine of 2 theta. The reason why that particular expression is nice is otherwise you will end with a trigonometry function with 2 thetas, which makes it kind of challenging to figure out exactly how it needs to look, but that will help.
So what are we trying to find?
The range equation. So I'll bring it back up here. So this was the height equation, the maximum height equation. That is the range equation. As I'm having you guys develop these, I'll just tell you right now, I do not want to ever see these equations be the first thing on your page. I want you to still start with all of the standardized projectile motion equations. Interesting. I thought for sure. Oh no, it doesn't. Oh no, it doesn't for that one, but not the other. You shouldn't be trig other than what I showed you.
I don't remember what you showed.
Okay, I'll write it back down again. Two times cosine times sine is equal to sine of 2 theta. You good?
I think so.
Okay. Time helper done?
Fine.
Okay. Sorry, future Eleanor, they're taking forever to do this.
And I used the trig identity. I did other algebra, so.
What's that?
I said I used the trig identity you gave me, and I did other algebra, so it should
And you've got the right answer at the end, so.
Hopefully. I didn't see.
That's right.
That's. Oh. Well, yes.
Is that the right thing you got?
Good. Very good. Which one? Oh.
I don't know why you do this.
No, that's not right. Is it?
Doing that thing you do, breaking my heart into a million pieces, like you always do. Yeah, you.
Or is it eight double time? It's just eight double time.
How do you go from this to this?
I subtracted. This is 0. This one is 0.
Oh, and why?
Yeah, because you have to go to the
All right, guys, I'm going to get going here. If you still want to work on it, that's fine. At the very beginning, because it's symmetrical, there's two different things that you can do. I'm going to do both of them real quick, just so you can see that. The first assumption that you could make is that delta y is 0. Out of curiosity, how many of you did this one? Okay, so none of you. That's fine. We could do that, okay? The other one that I'm guessing that most of you use then is the other assumption that you could make is velocity final in y is negative vi sine of theta. Did you use that? What did you use?
I know why I used the first one, just don't know what you meant by that.
Okay, well, I will show you both methodologies and how they result in exactly the same, okay? We are looking for delta time over here on the y-axis. So if I use this one right here, the equation that must be used is velocity final on the y equals velocity initial on the y plus acceleration times time. And thus this is negative vi sine of theta equals positive vi sine of theta minus g times delta t. Algebraically, when I subtract these over, this becomes negative 2vi sine of theta all over negative g equals delta t. Cancel, cancel. Yes? Is that what you did? Yes or no?
Yes.
No.
Okay, that's not what you did. That's fine. That's okay. The other thing that you could have done here, so I'm going to go back, is you could have also said that delta y is 0, in which case you would be using this equation. This would cancel the 0. This would be vi sine of theta times delta t plus 1/2 times negative g times delta t squared. Since this is 0, though, over here, I can divide everything by delta t. And then I can move vi over here, which would be negative vi sine of theta, multiply 2 on both sides, divide by negative g, and you'll notice you end up with the exact same thing. Is that what the first of you guys did? And what did you do?
So what I did, I just took the height or the df equals vi and just
Don't do that. Okay. The reason you can't do that is because technically you're right. The height should occur along that particular path. So you used the height and corresponding time with that and doubled it. Correct. That is, you're not wrong, but obviously you can see from this, you want to start from kind of what is more of a pure spot, given the information they have for you. And let's put it in another perspective. If you were going to try to find this equation, probably not a great idea to base your understanding of this equation based on a previous equation. You know, that's just going to mean more steps for you potentially in the future. But this is how you get to time. Once you have, you'll notice this was the time in both cases. Once you have that time can go straight in here. Delta x, or range, equals vx times delta t. Vx being vi cosine theta, and t, as previously stated, being 2 times vi times sine of theta all over g. So we come down here and reorganize. I'm going to put my vi's out in front. As there are 2 of them, we'll put squared times 2, this guy right there, times sine of theta times cosine of theta, which you can obviously see why I'm isolating that guy by itself, because now it is just vi squared times the sine of 2 theta over g. Okay, so let's talk about maximizing functions. And of course, I could make you guys do the optimization problems that with this wink, wink, nudge, nudge, totally possibility on the test. But let's just go ahead and talk generically right here about this particular function. Given a vi, some number, make it up, who cares, given g is 9.8, what, based on this equation, mathematically is the correct angle fire at to get the most range, and how come?
$45.
45. Why mathematically is that the correct answer? Say that again.
Putting in pi over 4 makes the argument of sine pi over 2, which is the maximum value of sine.
What are you doing radians, man? I mean, we're talking.
Because we
I mean, I get it, but like we're doing angles right now. Yeah, but
That's what
even
you
you
said.
guys don't get that. Come on. Say that.
Because if you put in 45 degrees, it makes
The,
it 90.
the
It's
max
90.
value of sine is 90 degrees, is 1, right? So you want sine to be 90 degrees, which makes sense. You know, if you look at our very next slide that we have right here, it's going to bring up the projectile motions for 45. What you can also see out of them is that the corresponding, the corresponding angles will in fact have the exact same range. The complementary angles are going to have the exact same range. Well, why? Because 30 times 2 is 60, and 60 times 2 is 120, and 60 and 120 are supplementary of one another, and thus are going to have the exact same sine answer. Yes? Okay? Now, if we go back a step, okay, use that same line of logic on the maximum height equation, and let's just go with mathematically first. What's going to give you the maximum height mathematically? 90 degrees. Why? Mathematically first.
All of it is in the y.
No, mathematically first. You're right, that is the... Because
sine
sine is going to be 1, and you, of course, know that conceptually because all of it's in the y, so it's going to max out the height in the y. Of course, that's not going to do very well for your range equation because your range equation is going to have 2 times 90, which, of course, is going to be the sine of 180, which is 0, because, of course, it is because you just fired the ball straight up in the air. It's not going to go very far in terms of range. Make sense? Now, in terms of calculus, what would you solve for in order to figure out what the maximum angle is here? Optimization, people. I want you to maximize theta. How can you figure out maximums? Take the derivative of. You would take the derivative of theta with respect to. So you know it's d theta, but obviously you always have to compare it to something. Now, you're regularly used to comparing it to time, but if you think in this particular scenario, do we compare delta theta to delta time? Is theta changing with respect to time? Well, sure, in the path, but this is the original angle that it was launched at, right? Is the original angle changing in time? No, that was set at a particular point in time. So, well, I'll let you think about that for later. Moving on. Maximum range, as it says, 45. Complementary angles will show the same range. Max height will be different for both angles. Times of flight will also be different for... Oh, I didn't do this. My apologies. We explained why this in terms of math, and then we explained why this in terms of real life. Okay. Why is 45, obviously mathematically, because it gets us a 90, but why is 45 going to maximize your range in terms of real life? Come on, baseball.
Oh, well, of course, because you're getting both distance and height, so you can get it over the wall and past the wall.
You're right. The idea, you got the right idea, but you said one of the things wrong. Why is y important?
For the time.
Correct. By increasing y, you maximize its time in the area. You don't give a crap about it because at range, it's going to end up on the ground anyway, right? So this is why, by the way, working my way backwards, I'm really proud of this. When I coached freshman ball, I was trying to figure out a good way at the beginning of the year to figure out how fast people threw, like how strong their arm was. And so I said, well, I didn't really have good technology, and even if you do have a good radar gun, there's a bunch of issues with it. So here's what I said to the freshmen. I said, freshmen, here you go. Here's a ball. I don't care how you decide to launch it, okay? But you only get like 2 steps from here to where you're going, okay? I don't care how you launch it. What you're looking for is max range. Do a little bit of math on this. Assume that they threw it 45 degrees. That's how fast they threw. In meters per second, multiply it by 2.25, 2.24-ish to get in miles per hour. And that gives me, so I can basically measure something in feet, divide it by 3.28 to get that in meters, multiply by 9.8, square root the whole side, and I can figure out exactly how fast they throw by just punching it in an Excel program that I already had on my phone. So ding, ding, you throw about 60 miles an hour. There you go. All right, moving on. Smarter, not harder. Projectile motion, you guys have been doing these problems. I'm not going to spend a ton of time on this. Non-symmetry projectile motions, as always, deal your y, deal with your x, all that sort of fun jazz. Are you going to have to use Pythagorean theorem? Sorry, not Pythagorean theorem, my apologies. You're going to have to use the quadratic formula? Yeah, you do. But to be fair, you already had to on last test as well. All right, so circular motion. We've done this a bunch. Basically, circular motion, what defines the difference between circular and projectile motion?
The acceleration changes with the...
Correct. Acceleration in projectile motion stays constant, okay? Stays in one direction. Acceleration in circular motion stays... Try that differently. Perpendicular to velocity, correct. Yeah, I mean, always parallel with force, absolutely, because it's going to go the same direction as force. But all right, so circular motion, I did this for you last year, but here it is again. This is the understanding, trying to get why the frick this equation right over here, which is what they will result into, why that results from the definition of velocity itself. The definition of acceleration itself. The definition of acceleration itself prior to doing circular motion last year worked just fine. We just took Vf minus Vi over delta t. And if that's the definition, we better still do that in this particular chapter. But what was different between one-dimensional stuff and what we were messing with here?
The acceleration might not be in one axis.
Well, it's definitely not going to be in one axis. You're 100% right on that. But what does acceleration centripetal change? The direction. What does it not change? Magnitude or speed. So when you look at that particular equation right there, if I attempt to use this basic definition for centripetal acceleration, it's not going to work, because here's what we used to do. We used to plug in 5 meters per second minus 3 meters per second over 2 seconds to get the acceleration. It's going to change by 1 meter per second squared. In other words, if an object is going this way with a particular velocity and has an acceleration that way, what we know is that velocity initial will change in that direction. There is your change in velocity. Yes? Since it's parallel, we can easily take 5 minus 3 to figure out that that change is 2, and then simply take that change of 2, divide by how much time it takes, and that tells us how much it changes every second. Yes? Now, when it changes direction, is there still an exact change in velocity? Is there a change in velocity? Yes, that's demonstrated right over here. If I was going up this way and I'm now going down that way, my change in velocity is still pointing from the original to the end of the final. From the original to the end of the final. But we need to figure out a new way to measure this change in velocity right here. Yes? Because we used to be able to go 5 minus 3. We can't do that anymore because what's happening with the speed? It's staying the same. So if I plug in 3 and 3, it's going to tell me that the change in velocity is 0, when it's not 0. But are the magnitudes changing? No. So here's what we did. Imagine you're going around a circle represented by this dotted line. Okay? Ri and Rf represent the initial position, just like they always have, but nicely in this particular case, Ri and Rf also represent the radius of the circle because it's circular motion. Correct. So what we have here is the velocity initial and a velocity final. The idea is we still want to use the exact same frickin' definition for acceleration. We don't get to change the definition of acceleration just because it's not working well for us. So how do we do that? We did exactly what I said. We took Vf minus Vi. Okay, so they do this a little bit differently than I do. So let me demonstrate how I would have done it. I would have taken Vf, just like they did, but what is minus Vi? What is a negative vector?
Yeah.
The exact same vector flipped in the opposite direction. So there is negative Vi. And this would result in the change in velocity. Now you'll notice that that methodology does work, but theirs is just fine too. I just did it a second ago. Change in velocity is how much change it goes from initial to final. From initial to final. And hopefully you can see these are completely the exact same triangle, just done from slightly different perspectives. Yes? Now, how much angle has changed? Well, that's easy. How much angle is there between these? If this is going around a circle and it's currently at, say, positive 10 degrees, and now, that would mean this location right here would be at what angle if this is at positive 10 degrees? What angle is this guy at?
100?
Yes, I almost said it poorly. I was going to say 110, but you are correct. Angle initial is 100. And if I said that's negative 10 degrees, then what's this guy here? That is 80, correct. Now you can of course see from this that this changed by 20 degrees, while this angle changed by 20 degrees, because this was at positive 10 and this is at negative 10. Okay, and of course you correctly got these angles from reverse engineering the fact that this velocity is tangent, plus or minus 90 degrees, right? This is just this minus 90 degrees. Why are we subtracting 90 degrees? Because we're going clockwise around the circle, and that's negative angle. Yes? So, what does that mean? It means these two triangles right here are completely similar to one another. You'll also notice, even though labeled differently, the magnitudes of these are the same. This is the same magnitude as that, yes? So we'll give it a different name. We'll call that magnitude VT. This is the exact same magnitude as this. We already said earlier, what is that magnitude called? Not RT, just R. You said it was radius earlier. So we set, well, they're not going to do it. They're not going to finish this off. That's stupid. So they set the ratios equal to one another. They said, all right, delta V over VT, delta V over either one of them, pick it VT, is equal to what other two combination of sides on the other one? Delta R over R. Now, the goal with this particular equation was to get it to use the exact same definition as acceleration. Yes? So, let's go ahead and isolate this guy right here by multiplying VT on both sides. And I'm going to isolate something for a reason to be seen in just a minute. So all I did here was just multiply VT on both sides, yes? What is obviously missing from the standard definition of acceleration? And this is where that understanding, this is where that understanding of calculus comes in. It's hard to see when you talk about this originally in AP1, but acceleration centripetal is basically equal, well, any acceleration is equal to the limit of this ratio as delta t approaches 0. Yes? So technically, when you look back at these, you got to remember that these are going to be a little bit off because delta theta is, quite frankly, too big. So what do? We smush these together. We smush these together. We smush those together as delta theta approaches 0 because delta t is approaching 0. That makes them perfectly accurate and makes this head towards what value? No. The arc length. Or what is the limit as delta t approaches 0? What is that? That's VT. Oops, screwed up. So we get acceleration centripetal is equal to VT squared over R. I did this explanation last year. I'll briefly go over it unless you, well, do you need me to go over why these match? Hey there, what's up? Hold on just a sec.
That's fine. Play for a time elementary kids.
Where's Grant and Jacob?
What?
Where's Grant and Jacob?
Oh, it is.
All right. I don't want to do this if it's boring to you. You feel like you don't know. Well, if it's boring, I don't care about that part because we're trying to learn. Anyway, but in other words, when you look at this equation, I should be able to say this. The speed doubles. What effect does that have on acceleration? Quadruples. Correct. The radius doubles. What effect does that have on acceleration? Cuts in half. Do you understand that? I get why you understand that over here. That's basic math. Do you understand why that happens in terms of this guy? I'm going to go ahead and guess no. So let's.
I don't get how
Oh my goodness. Okay, can I start by saying thank you? Okay. I'm so used to my first 2 hours not asking any damn questions when it comes to torque, and I know I complain about that, and I'm gonna stop complaining about that. So I'm gonna say positively, thank you. Like the fact that you just freaking stopped and asked a question in the middle of that is like so like, oh my gosh, this is so nice. This is so nice because I know I'm not perfect, so it's really nice when people do me the honor of being like, okay, we don't get it, let's work together. My apologies. Continue. What don't you get?
I don't get why the change in the limit as t goes to is that t goes to 0 or infinity? Zero.
As it goes to 0.
I don't get why that turns into the.
That's your basic standard boilerplate definition of velocity, technically, in this chapter. Let's go back here.
It's really going back, man.
All the way back. Oh,
Okay,
wow.
so
Oh.
Now, there you are. Okay, now, so that is the nice thing about this is it's not velocity tangential, it's straight up the actual velocity. For your purposes understanding here, what I told you last year that is 100% accurate is this, and this might be easier to get. What I said last year is I defined VT as arc length over time, which is not entirely wrong as long as it's constant, okay? Arc length being the distance around. Well, you can clearly see from these pictures that delta R, in order to be a similar triangle to that guy over there, cannot be arc length, right? But delta R is not arc length, yes? But it becomes more approximately accurate as the triangles get correct. So VT is how much of this area we're covering in a certain amount of time, but we need that time to be infinitesimal so we can talk about acceleration. The other thing of this that this does is if you're really careful with your triangles, you'll note that acceleration centripetal has to be pointed toward perpendicular, but also towards the center of the circle. Yes? And they kind of represent it well on this, that delta V is in fact straight down, because you'll notice they choose nicely symmetrical stuff so that delta V is straight down. But you do start to get in, well, wait a minute, why did I randomly pick delta V in the middle of it? Shouldn't it go here? Shouldn't it go here? If delta V goes from here, you'll notice, is it actually pointed towards the center? No. It's not, and it won't perfectly be pointed correctly in the right direction until you make it infinitesimally small, and then it will have the perfect direction of towards the center of the circle. Does that help? Cool. If not, please let me know. Oh my goodness. That was like such a freaking relief. I can't tell you. We're doing torque right now, and I told you I was going to stop complaining. I probably will. And it's just... There's obviously a discrepancy between the two of us right now, and I've tried to acknowledge that and be like, listen, this could be partially my fault. And I feel like what I'm getting from them is like, yeah, it's your fault. Awesome. Great. So right now, it's a pain in the butt because they won't ask questions, but because they won't ask questions, they're pissed off at me. So, yeah, it's fine. It's fine.
You should just perfectly know exactly what they don't understand.
Correct. Absolutely. That's what a teacher's job is to do. A teacher's job is to already know exactly what's in their head and explain it to them in exactly their way, despite the fact there's 28 different ways of understanding something in the room. And even if I do explain it particularly perfectly, I don't know if they just phased out on a particular question, which is completely understandable, but I don't know that. So apparently I need to have the intuition to know that, hey, Aslan was briefly on his phone because his mother contacted him for completely legitimate reasons during that fourth sentence out of 20 that I said. You recognize that that's the case so that I make sure to specifically address Aslan on that 4th out of 20 questions to be like, hey, this is what specifically you missed. Absolutely. Communication. Nobody's telepathic, people. Make sure you communicate with every relationship. Your teachers, your friends, your freaking, especially loved ones. Moving on. All right. Centripetal acceleration is, okay, you'll notice both of the sentences up there. Just a reminder of what I've said before. Acceleration centripetal is perpendicular. It's perpendicular. It's perpendicular. Perpendicular causes a change in direction. Causing a change in direction consistently means a constant change in direction and therefore ends up as a circle, because it ends up as a circle, perpendicular has also a tendency of going towards the center of that particular circle. Know both, but know that the beginning is that acceleration begins perpendicular to that circle. Moving on. Now, the good news for you guys is that this is probably about as complicated as an equation as you're going to use in this chapter for the most part. Okay? Period is simply defined. Period is simply defined as the amount of time it takes to go around a circle. So what is the distance around a circle? 2 pi r. Divided by, guess what velocity that is? Tangential. Because tangential, while changing in direction, is not changing in speed. Which means that equation right there is just your standard boilerplate constant velocity equation. Time is equal to distance over speed. That's all it is. Okay? So by definition, it's just the amount of time it takes to go around a complete circle. Of course, sometimes to calculate velocity tangential, you can work this backwards, right? You can say, hey, the velocity tangential is the distance around a circle, 2 pi r, divided by period. Like, for example, if I asked you to figure out freaking just how fast the Earth is going, all you would need to know is radius of the Earth, which is 4,200 miles, and how long it takes the Earth to go around, which is 24 hours.
Oh, you said how
I did say how long it takes the Earth to go around, to be fair. So that's answering a different question. Yes, around itself versus around the sun, we'll say around itself. So calculate how fast the surface of the Earth is going in miles per hour. I know this is an easy thing. Hopefully you understand that when hopefully you understand that when I do something like this, it's to transition it into a less easy thing.
Oh no.
What's that? Approximately 1,100 miles an hour. Are all points on the Earth going 1,100 miles an hour?
No.
No. What is the only spot on the Earth that is going, well, not the only spot, the set of spots going that fast?
The equator.
Right.
The equator.
The equator, correct.
Oh.
Okay.
Yeah.
And, excuse me, that based on that, there is a set of locations on Earth that are going 0 as far as that's concerned, which would be
Oh no, pole.
the poles, correct, standing at the poles. So, what other information would you then need, what basic set of information would you then need in order to calculate how fast we're going here in Alton?
The degree of where we are.
So you would need what distance? That seems, kind of complicated to figure out. I don't have that just off the top of my head. Try again.
Latitude.
There it is. How do you do the different ones? Do you remember the different ones?
The longitude is this.
Latitude makes a ladder.
Oh yeah. That's
Latitude makes a ladder. Longitude's the other one. All right. So here you go. According to this guy right here, Alton is roughly. I used to have my bracelet. I have this really cool bracelet. I still have it. I just don't wear it all the time. It has the latitude and longitude of where I proposed to my wife. It's kind of cool. That's fine. Anyway, but let's go 38 degrees of latitude. Calculate then. See if you can't figure out how fast we are actually going here. You're going to want to draw a picture on this one.
Does that count? Is it from the pole or from the equator? Is it from the pole or from the equator?
From the equator, yeah. 0 is here, and it goes up to 90, down to 90.
We're only 38.
Zero is where?
What really messes me up when looking at the 0's equator. So 0's here. So we are and this is for very purposeful reasons, the equator being 0, based on what we're doing right now. And 40th,
Okay, yeah.
40th is like Springfield. Springfield's about 40th. So yeah, so we're about 38th in this particular spot. What really messes with me is this. Canada, let's go with like baseline Canada, like a little bit above the border is around 50. Okay, this is 50? The bottom of Great Britain.
Really?
Great
Yes.
Britain and Canada are at pretty much the exact same latitude. Like here you go. Look at this. Look at this. Here is bottom of Canada. Bottom of Canada, 50, kind of stretching up to 60 right here, right? So the heart of Canada between 50 and 60. Go over to Great Britain. Bottom of there right there. 50, 60. They're basically at the exact same spot. So why is it that when you think of Canada, you think cold, and when you think Britain, you think kind of our similar temperatures?
Wind. The Mediterranean Sea.
It's the water.
It's the water.
Close.
It's the ocean. Didn't we talk about this earlier in the year?
Might have, probably.
Science.
So,
I'm fairly certain we did.
Science.
what's your name?
Oh crap. Okay. Okay. Thermodynamics. Like, come on.
Yes, no.
Come on!
Yes, no. Yes, no. Yes, but essentially the only thermodynamics is simply put, the water is hotter there. Why?
Because of the
Coriolis effect. What we're describing right now means as the Earth rotates towards the east, because the sun rises in the east and sets in the west, which water is going fastest?
equator water.
Equator water, based on what we're talking about right now. The water up here is going slower, which means since it's going slower, it creates this sort of circular motion in the water and the seas. So if you're over here in Canada, the water up here is going to go down,
Chili water.
which means you're getting that chilly water. That's right. But if you're over here on the east side, water is coming up, you get that toasty water. That's right, toasty water. So London is hotter than also extraordinarily rainy due to the hot water coming up into a cold frigid temperature. All right, so what do you got? How fast is it?
93.5.
No.
866.
866 is correct.
How do you do that?
Well, he said that the equator is 0 and was the fastest, so I knew that we had to use it.
What you needed to recalculate was the radius. The radius being the distance from the point of rotation. Yes?
I didn't do that.
So, if, hold on.
So that's really easy actually to figure out.
Well, yeah.
So which part of this triangle do I know?
The angle of that.
Right
The
there.
angle that is 38.
So the
And you know the
Radius.
Which means you know the other one.
hypotenuse is
Or radius.
4,200. Now that is roughly an approximation. Technically speaking, due to the Coriolis effect, the center of the equator, it's not a perfect circle. It actually bulges a little bit in the center. Now, when I say it bulges in the center, here's what I want you to understand. Our planet is more circular than any ball that you have ever seen ever.
You mean more spherical?
Thank you. Yes, more
And
spherical
smoother.
than any ball.
Smooth.
And that's what I was going for.
Yeah.
Smoother. To put that in perspective, if you took, gosh, what is it?
Mount Everest and the Mariana Trench.
Yeah, on this level, it would be absolutely nothing. You'd run your finger over the top of it, and you would feel it as like more smooth than probably anything that you felt as smooth.
I
Yes.
think I saw somewhere that if you resize the Earth to about the size of an apple, the Himalayas would be like a couple micrometers high.
It's not, yeah, it's not much. It's not much. It would never be noticeable by a human. All right, so that is to point out some cool stuff about calculating velocity tangential. I think that particular one might come up in your problem. Now, let's do this. Let's say you're dealing with a roller coaster, okay? And on this particular roller coaster, you'll notice, by the way, this AR right here also stands for acceleration radial, okay? That is the exact same thing as acceleration centripetal, just means it's along the radial direction. Now, you know, for example, that this particular guy right here has an acceleration upwards because you look at the circle. Even if you couldn't see the circle, you could see that the velocity is changing from tangential this way and is curving up. Yes? So since it's going up, we know there's an acceleration upwards. In addition, you would also have to know in this particular circumstance what's happening to its speed. According to this particular picture, this particular thing is changing direction upward and speeding up. So acceleration centripetal is perpendicularly up to the velocity. Acceleration tangential is parallel, pointing the same direction, so you should be able to look at this and say, hey, this is changing direction upward and speeding up. Yes? This is acceleration tangential, change in speed. This is acceleration radial, also known as centripetal. And acceleration is actually the vector addition of both of them. Now, you will be asked to do this, but great news here is how do you calculate acceleration centripetal? Whatever the current speed is, the instantaneous speed, because obviously due to this guy, it's about to change. But you can take vt squared over r at that spot. How could you calculate acceleration tangential? Your basic definition of change in velocity over time is going to help you along those fronts. If you have both of those two particular equations, how will you get this guy right here? Pythagorean theorem and inverse tangent. Make sense? Okay, and you should be able to look at a situation right here, and basically I should be able to go, hey, at spot B, what's the object doing? Going down, and what's going this way, right? And it's, well, easy thing to say is just change it. This is changing direction upward, this is changing direction downward. Okay? In this particular case, you'll notice this acceleration is very similar to projectile motion, just gravity, right? What is happening with projectile motion right here? Well, this particular thing is speeding it up, and this particular thing is changing direction. Let me ask you a question without any background. In projectile motion, when does the object change direction the fastest? At the top or the bottom? Where does it change direction the fastest? The top. Because originally, let's say I make an object go, let's say I fire an object off of the building going this way. What's it going to do? Okay, as best as I can, that is a parabola. Where is it going to change direction the fastest? Top. Why? Because the acceleration is, for the most part, perpendicular. Where is it going to change speed the fastest? The bottom. Why? Because acceleration is mostly parallel to velocity. Acceleration stays in the exact same direction, but since velocity is changing, it gets perpendicular up here, which all of it perpendicular means all of that centripetal, till it starts to go practically the same direction. Now all acceleration is basically tangential. And in real life, eventually it does become all tangential because air friction eventually causes whatever was in projectile motion to fall straight down. So, moving on. So total acceleration is just the vector addition like we were talking about right there. Boom, boom. All right, so total acceleration equations. Acceleration total is the absolute value of dv dt. Acceleration radial, okay? Negative acceleration centripetal, okay? And the total acceleration, I don't like that at all. Just do the same thing I've always done, which just that just defines acceleration, excuse me. The reason why there's a negative here, I'll explain this in just a second. Just do this, do what we did last year, say acceleration is towards the center of the circle is positive, okay? The reason why this negative here, it's icky, is because if you, acceleration centripetal by definition is this equation, yes? R up there is technically not radius. R is the vector pointing from the center outwards, yes? So in other words, if this is your circle that you're going around, R is that way. It's pointed outwards. Which way does acceleration point? Inwards, which is why this negative is technically here to cancel the negative on R right there. Does that make sense? You can easily solve that by just saying, hey, towards the center is positive. Done. You're all set. And like you see here, Pythagorean theorem and direction, inverse tangent, and all that fun jazz. Relative velocity. I think that the best case scenario here is me flipping through this real fast, and then as you guys have questions on the homework, you asking me so that I can be done a little bit quicker here. I thought this was going to go a little bit quicker than it did. We've already had these conversations in general. We talked about them when talking about special relativity. This was the whole, Matt and I moving next to each other situation, where even though you see Matt and I both going this way, remember this? Matt, was it you who walked? Yeah. Look at this. Yeah. Matt was walking faster. So to Matt, what am I doing? Going back the opposite direction. Yeah. And it's really wrapping your head around there. Particular reference frames. So what they do What they do is they talk about two different reference frames, and those reference frames are separated by the relative velocity to them. And reference frames are one constant velocity versus another constant velocity. We currently all share the exact same reference frame because we are going the same velocity. Okay? If Caleb, stand up real quick and stand next to me. Hustle up, let's stop here. Okay? Caleb, we're just going to walk across the room together, buddy. Okay, you ready? And here we go. Are you having a good day? Excellent. Very good. Awesome. Okay, have a seat. All right. As we walked, I know it was necessary that we did that. As we walked across the room, how fast were we going relative to each other? We were in the exact same frame of reference, just like all of you in the exact same frame of reference. Now we can feel in our legs that we were pushing on something, so we get the general gist. Most people standard believe that that means we are moving, but physics says it don't care. What separated your frame of reference from our frame of reference? The relative velocity between the two of us, right? In other words, I could either say, let's see, the standard frame of reference of S for superior, okay, to I in inferior, the people that were moving versus moving, was either +2, okay, from your frame of reference, or you were -2 relative to our frame of reference. They represent that visually by saying this: you guys are in position A. Yes? We were in position B. Okay? Let's try that one more time again, Caleb. Okay. I'm going to stand over here. Okay? All right. So now walk at a relatively low pace. Okay? And go. Okay. Now, I was attempting to give 2 dimensions to this. What did you guys see me doing?
Rubbing up against the wall.
Come on, come on. You saw me going this way and this way. What did he see me doing?
Just going that
Just
way.
walking into the wall. Straight up just walking into the wall. That's it. Okay, and that's what can be seen here. The frame of reference between the two of us, Caleb and I, somewhat shared this B frame of reference. Now, this is not quite the same. He would have seen me going this way to where you see him. So in this particular case, Caleb would see me getting out in front of him a little bit and going that way, right? But you would see me as a combination of Caleb's reference frame B and what I did relative to B. Does that make sense-ish? I'll tell you, the thing with relativity in general, not even special relativity, that I have found is that, quite frankly, when you actually get this, concepts aren't hard, but your brain is not freaking programmed this way. So it kind of takes breaking your brain over and over and over again against these ideas and messing around with them and going, okay. Like understanding the phrase, I've done this 1,000 times, so I'm not going to do it in here right now. Understanding the phrase, there's no such thing as slowing down. And going, okay, here we go again. And the 10th, 11th, and 12th time doing that is finally, like, in getting there is finally, okay, this is not that hard, but it is. Your brain doesn't naturally default to thinking in this particular mentality. All right, I showed you this last year, but here it is once again. Proper notation helps a crap ton with this, okay? First subscript represents the object being observed. If you want to put it a little bit more simplistic, the first subscript is the object moving. The second subscript is what it's relative to. That does not mean what it's relative to isn't moving. Okay? Again, let me say this, there is no standard zero. Okay? If we have a velocity of Spainhour relative to Earth of +2 meters per second, all that means is that Spainhour is going that way relative to the Earth, but physics is fine saying Spainhour is doing what? Holding still, in which case, I'll go ahead and do it for you real quick. This always messes with my mind when I flip my perspective to do this. All right, guys, I'm not going to move. All right, here we go. I got you. All right. Took me a minute to get the Earth going that way for you, but I'm in the same spot the Earth went that way. You cool with that? It's messy when you think of the world in that particular. Think about that today. Imagine you will, because you can represent this. The perfect demonstration of this is if you have ever done anything with VR, okay? And you see those people, especially like walking around on VR. The reason that works It's because your brain doesn't know, because there isn't. And it's not your brain's fault here, it's a straight up fault of physics. As long as you are pushing going that way, it doesn't matter that you're not going anywhere. If you feel you're pushing going that way at 2 feet per second, you're going that way at 2 feet per second because something is going that way at 2 feet per second. And whether or not your brain knows that that's actually the Earth, or whether that's actually on some treadmill and the treadmill's doing it, doesn't freaking matter. Now the treadmill, of course, counteracts whatever you're attempting to do to keep you at a zero relative to the Earth, but that's why your brain doesn't know, and why it's super messy when somebody messes around with VR next to you. Anyway, and here is what I showed you guys. Well, no, these are just relative equations real quick, but this is just basic velocity equation right there. This is what you really, they use u at different times to talk about the derivative of position, but the main thing to get here is just this, okay? So this is the velocity. This is what they talk about being the one that separates the two stages of A and B, and u is defined as the actual velocities that are technically moving relative to each other. As it will, what you would say is, in that scenario where Caleb and I were walking across the room, that velocity is arguably set for the situation. Okay, that is a constant velocity set for that situation. U is how fast I am going relative to that frame of reference. Okay, so this is person, or Spain-Hour in this case. So in other words, here's the generic way to do it again. The velocity of Spain-Hour compared to Earth is equal to, actually they want me to use U. I'm not going to, suckers. The velocity of Spain-Hour compared to the frame of reference with Caleb, plus the velocity of Caleb's frame of reference to Earth. First and last, first and last. Third frame of reference in the middle, third frame of reference in the middle. Now you can start to mess around with this a little bit. You can start to do this. How fast was Spain-Hour going compared to Caleb? Well, we can just do some simple algebra. Sadly, these are vectors, so simple algebra is not simple algebra, right? So to get this by itself, we subtract that on the other side. But what does that mean as far as subtracting vectors? Those are not just nice numbers. Those are x's and y's and all that sort of fun jazz added in. So you got to do. Now, maybe you don't want a negative in there. All right? You don't want a negative in there. Well, you'll remember that we have this frame of reference as well. The velocity of A to B is equal to the negative velocity of B to A. All this is simply saying is that A to B is here, B to A is here, and by putting a negative, what does it do to one of these? Flips it so that they're going the exact same direction, which means I could replace this with what? So this would be the velocity of Spain-Hour to Caleb is equal to the velocity of Spain-Hour to Earth plus the velocity of Earth to Caleb. Make sure I do that right here. So in my analogy, for example, okay, Caleb and I went this way. I went this way compared to Caleb. And this is what you saw. Label each part of that triangle for me. This is the way Caleb and I went, so that would be the velocity of. Assume, by the way, Caleb is the one holding that frame of reference that we originally walked on. So this is the one where Caleb went that way and I went. What's that? No. This is, okay, again. Caleb went this way. You saw it. I went that way, but to Caleb I did this. So this is the velocity of Caleb to Earth. This is the velocity of.
And that's Spain-Hour to Earth.
Velocity of Spain-Hour to Earth is equal to Caleb to Earth plus Spain-Hour to Caleb. Or, if you want to do this, if we want to know what Spain hour is to Caleb, we take Spain hour to Earth, this guy, and then we add Earth to Caleb. But if Caleb to Earth is that way, then Earth to Caleb is... Is that the exact same thing as this?
Yes.
Yes, it is. Accelerations from different frames of reference. Ooh. All right, so the derivative of the velocity equation will give you the acceleration equation. The acceleration of a particle measured by an observer in one frame of reference is the same as that measured by the observer in the other frame of reference at a constant velocity for the first frame. That's confusing. Why is that confusing? Well, it says the acceleration is going to be the same for both of them as long as velocity is, which is messy, but essentially all that says is that, yeah, we'll agree that acceleration is 0 when we're both traveling a constant velocity. What happens when we start changing those velocities? Then you start heading into general relativity and the curvature of space-time, which is beyond the scope of this particular course right now, so we're not going to mess with that, because quite frankly, you have to start to deal with vectors in 4 dimensions, and via my work on it is a pain in the tail. I'll tell you math that will be painful, just as kind of like bullet points, like if you guys continue forward in this, Hilbert matrices and linear algebra, specifically matrices, and the rotation and variable nature of them is, it's just, you have to straight up do vectors in 4-dimensional space in order to properly understand what's going on here, which the math by itself is mind-melty, and then that's just the building block that you have to understand super well to get into the mind-melty nature of how, like, and I can tell you that, you know, what you already know, but, oh, there's a curvature of space-time, and gravity affects the curvature of space-time, but then you have to get into understanding truly what space-time is, and, well, we're not going to worry about that for right now. So there you go. Acceleration is the ratio of these, but look at what we got here. What is true of this velocity? What is true of the velocity between B and A? What was the true of the velocity between, excuse me, between Caleb, myself, and you? As we walked across the room, what was true of our velocity? It was constant. So the derivative of said velocity is 0. So the derivative of the changing of my velocity with respect to him, if I accelerate relative to him, you should agree with the exact same acceleration. In other words, if we do that thing again, and I had enough space to walk here, but like accelerate that way, like speed up going that way while maintaining a constant velocity here, both you and Caleb would agree that I accelerated that way, right? If I speed up going that way and that way at the same time, my acceleration would go like this. He and you would agree. Why? Because he is at a constant velocity to you. Yes? So the derivative of Caleb with respect to you is 0. Thus, the derivative of what Caleb sees me do with respect to time is equal to the derivative of what you see me do with respect to time. So, will you and Caleb agree about my final velocity?
No.
No, you will not agree on my final velocity. You will agree on my acceleration. So essentially, easy way to put it is, you and Caleb would disagree about initial velocity, but the change in that velocity would be exactly the same in both the x and the y. Or, let's put it real simply. Let's not do 2 dimensions, let's do 1 dimension. Okay? We're moving at 2 feet per second relative to you. I accelerate at 3 meters per second squared that way for 2 seconds, changing by 6. We started at 2. We should end at 8. For who? For you. You would see me at 8. But for Caleb and I, who are both at 2, we are what relative to each other? We're 0. So when I accelerate at 3 for 2 seconds, I would change by 6. So Caleb would see me go at, so you would be seeing me go at 8. He would see me going at 6 from different relative points, but you both saw me accelerate the same. I'm done. I believe. Let me make sure. Yeah, I'm done. Bye, Eleanor. Hope that was fun.